All right, so we're going to look at the Epsilon model, and it should be noted that probably the Epsilon models in practice and implementation are one of the most popular models like K omega. But, you know, looking at that dissipation equation, which is repeated here in 6.28, it's way more complicated than the omega equation. But the good thing, if you look at it that way, is that it's derived from the equations of motion, and omega is almost like a postulated equation, like we discussed last time of Kolmogorov's equation. But it has way more terms, and it's more complicated, so I guess it's a little bit more difficult to model. And, you know, the closures we have today, there's sort of some advantages and disadvantages practically about which model might be more useful. So just a little bit of history. Well, first, you know, we showed some of these equations previously in 5.8, 5.11 from the previous section. And in our class development way back when we formed these equations, we talked about them too. The most popular form of K epsilon equations is called like the standard K epsilon model. And that form of the equations is the paper I just passed out. And we'll look at that real briefly here. And that was published in 72. And probably the earliest model was by Chow, 1945. That was a K epsilon model. And there's other earlier ones, but they weren't seen as standard, and they actually had some terms which I guess were seen as missing. And the one in Launder and Sharma, that was in 1974. That was published, but it was aimed for rotating disks. And when they formulated their model and validated it for rotating disks, as you see in the paper I passed out, they actually used a bit of a different closure and a little different form, which is what most people use today to start with epsilon models and closure. And of course, an advantage is you have a epsilon model itself is derived from moments of the Navier-Stokes equations, which I think we talked about maybe in chapter 2 or module 2 of the class. And just here's a reminder of the operation. You can find epsilon is derived by taking the moments of the Navier-Stokes equations. And way back then, I'm not sure if you remember, but this mathcal or math script n is the Navier-Stokes equations operator. And so we're doing partial ui partial uj times partial xj of Navier-Stokes, set it to 0, and that's really the major operation that we take. And through the steps, which we talked about previously, you get this equation. And you can see it's an equation for dissipation. Of turbulent kinetic energy. And that's all it is. And there's tons of terms in it. And the major terms in 6.28 are production and dissipation. Right. There's going to be even a dissipation of dissipation. And a sum of molecular diffusion and turbulent transport of dissipation. So you see a term like this, dissipation of dissipation, that seems a bit confusing. But it's like the rate at which the turbulent kinetic energy is dissipating. So it's a transport model for the rate of dissipation of TKE. And so it has like a units of basically TKE per second, because it's the rate at which TKE is dissipating into heat and, in a real flow, also acoustic waves. So where does the turbulent energy equation go? Well, through the viscous action, it's being converted mostly into heat, like 99.9%. And a tiny, tiny, tiny little fraction of the turbulence is radiating as acoustic waves, which I guess is the whole point of aeroacoustic theory, is trying to understand how turbulence is being transitioned into acoustic waves. And a lot of people have spent a lot of time. If you look at all these correlations, you can view them as additional unknowns. And a closure should try and relate those double or triple correlations in all these forms, like pressure, velocity, triple correlation of velocity, into what? Relations to variables we know, like mean flow variables, or other variables like K and epsilon, I suppose, ones that we can solve for in our equations. So that's a monumental task, and it's pretty difficult, but thankfully today, to study these things and find what all these correlations can actually look like, well, you can always do DNS. That's one trick. So a lot of people are doing DNS research today, but it's at low Reynolds number because our computers aren't very large to actually calculate all these terms and find better correlations. Or you might combine that with machine learning. To try and find better flows. And there's large databases online where you can even, like say from Johns Hopkins Turbulence database, download like boundary layer, wakes, channel, flow databases, and you can actually have their computer generate these correlations for you to see what they look like. It's actually kind of cool. And that's done as like a research or community resource, sponsored by the federal government. Just some notes about these K-epsilon equations. I mean, we really haven't done much with them. And the closure approaches are much like we talked about with, like, say, the Wilcox K-omega model. They use the same types of flows, the same types of closures, right? You got homogeneous decaying isotropic turbulence. You got boundary layers, and those are the two main ones people look at. But people, just like K-omega, try and find closure based on many different types of flows. So generally the same closure procedures are used for K epsilon as K omega, and they might focus on flows like the boundary layers in the log region or wakes and maybe grid turbulence, and you can focus on one or many, and ideally you would have one type of flow per closure coefficient, but that doesn't happen in practice. And the epsilon equation is much harder to close. And the standard closures for K omega and K epsilon result in better predictions in different flows. So something we often notice is that the K omega like closures are more predictive in the boundary layer, but K omega epsilon seems to just be in general more predictive in the outer layer or free stream. In fact, the standard K omega models have numerical problems sometimes out of the free stream. So some people immediately saw, well, there's advantages for predictions. This just might be because of the form of the equations and numerical implementation in different regions of the flow. So they say, well, why not try and take advantages from one equation and the other and somehow combine them? And those were called blended approaches, or zonal. And so those are ones we want to kind of look at. As far as closure, we know that the epsilon equation represents dissipation of TKE. And it's, as I mentioned, I'll just write very difficult to close, but I've already mentioned that. And so just based on these notes, before we get into, well, yeah, let's look at the standard model. I have that here, and I'll actually bring up the paper. So this, as I mentioned, is not the first paper, but this is what we call the standard model. And that's the paper I passed out. And you can see it has very little, it's a very short paper. And they quickly describe how their set of K-epsilon equations are a little bit different than the ones published originally and put forward by, say, Chow. And you're welcome to read through it. It's very short. That's the abstract. Now we'll look at the paper in a second. And I've repeated the equations here in a summary format. The eddy viscosity, diffusivity, and here's the K equation, right? And here's this form here in my slides is wrong. This is actually the dissipation equation. And we'll look at that. And I guess I didn't update my slides, right? So this is not the updated slides. I updated my binder and the class notes that I gave you, but not my own, I guess. That's a little embarrassing. But take a look at that. That's repeated. And let's go in here and say, okay, well, what's different between this K equation and the one originally proposed? And this term here is really a new source term in the K equation, if you compare these papers. And it's not fictitious or anything. It's just when the original folks were looking at these, they were neglecting certain terms because they were only interested in calculations of boundular flows. And these two authors were interested in looking at flows on, say, a rotating disk, like this, in just a quiescent environment. And as this disk rotates, then there's very large flow gradients that are forming on the surface. And this is an interesting problem because it was studied by Theodorson, who is a NASA Langley researcher, and he actually made big strides in early turbulence models. And but he's really known in aeroelasticity. So if you've ever taken an aeroelasticity class, you know, to study how airfoils are stable in flows and how flutter occurs, you'll see something called the Theodorson function. And that's named after him, and he did some analytical work on these flows. So when we look at the paper quick, we'll just take a glance at that solution. And then here's the closure coefficients they recommend. This is a Reynolds type number. See, it goes as density K squared over viscosity. And here's their proposed closure coefficients. So from that point of view, it's actually pretty simple. And a few notes of how it differs. Well, one, there's that extra source term, which I just marked. And there's a turbulent Reynolds number in their closure with slightly different coefficients. But you'll see that if you look at many, and probably hundreds, literally hundreds of different K-epsilon models and closures, they may not have this. Some will have wall distance models, some will be blended with other models, some might be detached to these simulation combinations like LES-RANS approaches. And so don't take these to the bank, but this is kind of seen as also the standard original closure. And let's take a look at the paper. Oh, I should say also D.C. Wilcox in his book gave this summary. So I took the equations from D.C. Wilcox's book for the summary of K-epsilon, and he wrote them this way. So see, now I have the epsilon equation, which is good. And see, in this form, this is what is seen as the standard model, which most people, when they want to do a K-epsilon formulation, use these two equations in conjunction with the Favre-averaged mass, momentum, and energy equations in a gas law. And then you have a fully closed set of equations. So if you wanted to create your own K-epsilon closure, because you think you can do better than, say, Chien's model, like if you get up ANSYS or star CCM today, you'll go into RANS models, two equation, Chien, that's probably the most used one, and you can try and beat them, which is kind of cool. And here's your starting point. And I noted this is the standard model in your notes. So there it is for your reference. And let's go and look at his paper briefly. So let's see, Launder Sharma. So there it is. Letters to heat and mass transfer, very short, 7-page paper roughly. And this is just repeating exactly what I said. This is the equation I didn't have typeset in your notes, or my notes, but should be correct in your page. You see it's pretty big. And this is in a cylindrical form. Why? Because they're looking at this rotating device. And just for fun, just real quick, let's go down and look at some of the results. This is the radial position versus velocity on this spinning disk. And they have their predictions with measurements at Reynolds number 9.93 times 10 to the fifth. And this was actually studied with a coefficient of torque versus their predictions with Epsilon. And here's the analytical theory of Theodorson, which I mentioned. That's what these dots are. And it agrees pretty well, especially at higher values, 10 to the 6. Anyway, the paper, the paper is interesting because it's just basically saying we took the original formulation of K epsilon from two authors, Jones and Launder, which is one of the co-authors originally, and they edited them to have this extra effect, and they rewrote it in a standard form, which is seen as the standard K epsilon model. It's that simple. So it's worth reading a short paper like this, but it's definitely not in-depth paper. It's very mathematical and justified that way. So anyway, that's all I really want to say about K epsilon models. Now you can say to yourself, well, you can choose any two partial differential equations to close your system. This is a two-equation model. And people almost always track K because it's just the trace of the Reynolds stress transport equation, right? So then you always say, well, what do I want to do for my second equation? You can choose anything, and we chose a lot of different properties. And if you go to Google Scholar or AIAA, research website, arc.aiaa.org, and just type in two equation models, you'll get tons and tons of results, and you'll have every variation for a second model under the sun. So people have tried a few, and I just want to make a note of a few of these models. And obviously the first two equation model is Kolmogorov, so that started all. And the big criticism of the omega model is it's sort of put together by dimensional analysis and not rigorously defined. And the epsilon model was kind of found mathematically rigorously, but it might be harder to close. But why not choose other turbulence variables which are kind of easier to measure with 2-point correlations? Right? And what would they be? Well, one would be a length scale. And the other one would be a time scale. So if I have two hot wires in a turbulent flow, I can usually measure length scale by varying their distance in a turbulent, statistically stationary turbulent flow. And in the other case, I can just use a single hot wire and look at the autocorrelation and find a turbulent time scale. And so people said, well, why don't I use this idea? Because it's something I can measure, because I can't really measure dissipation. Like, how do I measure dissipation experimentally? That's very difficult to do. And how do I measure specific dissipation, like omega? That's also very difficult to do. But I can easily measure these two quantities. So it makes sense, like from an experimental point of view, to make predictions against something you can validate. Like we can certainly validate against K, right? Because I can find the TKE with, say, a hot wire. But not so much things like dissipation or specific dissipation. But I can look for L and tau. So if I make predictions with like a K and tau or K and L model, I might have a stronger case to validate them against experiments, especially where I don't have analytical solutions. So that was, I think, the motivation behind these types of models. And let's just look at a few, the most famous ones. One in Rada in 1968, he had a K, so he used the same K equation. And then he had another equation, which is the turbulent length scale times K. So it's not just L. You can find L models, but this is a KL model. And why is that? Because it just falls out of the equations a bit easier. He defined the 2-point cross correlation, which we looked at earlier in the class, right? That's just U, I prime, U, J prime, and it's at two spatial positions, X and X plus R, okay? And it's the same T, and from this you can get lengths. In fact, you can see K times L in certain fields goes as 3/16 times the integral of the trace of this tensor at position x, t, and r, integrating over r. See, there's r. So that's how you define KL as a quantity, but then of course you might, in some cases, you might need this Reynolds stress tensor. So you might say, well, what's the advantage? Well, obviously experimental comparisons, right? Because I can do the same type of measurement and estimate L's by integrating over a distance. But the disadvantage is it turns out that the predictions aren't really better or closures than the K, just the standard K epsilon model or K omega. So they're there, but it doesn't seem like it was a lot of extra work, and it's not widely used except for maybe a little bit better experimental validation. And here is Rada's 1968 model. And you can see it's an equation for KL. So what do you get when your code ends? You're getting turbulent kinetic energy K in space, and you're getting L in space. Okay, so then the K epsilon people will come back and say, okay, so you directly predicted L. And I would say if I was a K epsilon or K omega proponent, which I am, I would say I can just calculate L from K and epsilon, right? So I would just say, big deal, you calculate L in space. I can just do L equals K to 3/2 over epsilon, and I'm done. So I can also find a length scale in space from a steady round solution using a commercial solver. I don't need this KL type model. And I could say that about a K-tau or K-tau model. Okay, and you know, it's the same type of thing. You have the same types of closure coefficients. Other people looked at these types of models, and probably most famous one, I think, is Rody Spalding. If you want to look them up, that was on page 1970. And I saw the most recent publication, so you see the research is not active in KL models anymore, 1994. At least my Google Scholar search, and excuse me if there's newer ones. So anyway, there's some closure coefficients. Another disadvantage is some of these researchers like Nig and Spalding, he says, wow, some of these closure coefficients might depend on distance from the wall in a KKL model if you want to have good agreement with, you know, a wide range of experiments. So that's another disadvantage. You could say it's not truly a closed model, even though it's a two-equation model, to have good predictions. So that's where I don't know how this can be explained easily. Maybe one of you has an idea of why like a KKL model for good agreement would need kind of a non-closed form. Well, it is, of course, it's non-closed form, but a non-closed turbulence model. Okay, I'm sorry. The closure is fine. What am I trying to say? It depends on the solution in advance. So, excuse me. Okay, then you say, okay, well, what about a K-tau model? So that's the other choice. Well, we just kind of look for an autocorrelation now. It's like a 2-point space correlation, but now we have a 2-point correlation at 1 point in space, and we vary time. So see, now we are varying over T prime, or T, at location T prime. And if we look at that, we can form a K-tau model. So here's our standard form for K, the trace of Rij, and K-tau would be 1/2 of the integral of Rii. Okay, so this is a whole nother class of models, and I think the first is by Zierman and Wolfstein. And this is their standard closure, same type of eddy viscosity here, coefficient times turbulent kinetic energy times tau, which is the time scale. And we have a turbulent kinetic energy. And now we have an integral or time scale type model. I'm not sure if it's good to call it an integral time scale, but it is a time scale. I've heard people argue with me about, I guess, if these things are time or or integral time, which is the largest time scale of turbulence, or if it's just a time. And there's particular closure coefficients. Oh, and this equation's wrong. Sorry, I should have the closure coefficients here. I need to update my slides. It's my note. Here's the k-tau equation. So once again, transported k-tau. Tau is time, tau ij is stress. And, you know, I can sit here and make the exact same arguments for and against it. One of the variables I'll get is a time scale, which is nice, of the local turbulence quantity. I'll have that everywhere in the flow as a function of space-time. And I'll also have turbulent kinetic energy. And I can directly compare these using a measurement technique where I just put a hot wire in the probe and find an autocorrelation and estimate the time scale. And I could directly compare them, and that's wonderful. But once again, I could say, well, I have a k epsilon or k omega model already implemented, and I can write tau, the time scale, as a function of k epsilon or k omega. So those are just some disadvantages. And there's not a whole lot of research today. Like if you want to get a research grant in fundamental research like at a university and study like alternative RANS models, it's very difficult to get one because all these turbulence experts on the NSF panel will say, well, what are you going to do that's new that hasn't been examined or tried for alternative RANS equations? And that's a very, very, very hard argument to make. So most people have focused their energy on trying to close or use as a starting point k epsilon or k omega models. And they've been explored extensively. But we know there's actually disadvantages and advantages to k epsilon and k omega, like I just noted, right? So you might say, oh, well, maybe near the wall I would prefer to use a k omega model, and out in the free stream I want to use a k epsilon model. And then you can say, well, how do I combine the two? And how do I also try and better predict, like the Johnson-King model, separation and shock boundary interactions, which wasn't really improved upon in any of these models. At the time of the publication, acceptance of like k omega and k epsilon, these models did not have the closure and physics in them because they're not tracking Reynolds stress. And if you remember our discussion of Johnson-King, they tracked Reynolds stress, but it's an algebraic model. And it was really a model which I think was most successful in predicting adverse pressure gradient, even with the publication and validations of these models. Now remember when we were talking about Baldwin-Barf model at NASA Ames, they let two people review their paper. One was Spalart, and we talked about Spalart's model, and the other researcher was Florian Mentor. And that's where the combination of k epsilon and k omega came to be, and what he created was called the BSL model, which he calls the Mentor or Florian Mentor baseline model. And it's simply the combination and blending of k epsilon and k omega.